Okay, so I already explained the problem, and we know here in this problem that we have a turn with 25-meter radius. We know that the car is traveling 11 meters per second, and the coefficient of static friction is 0.70. So let's go ahead and draw out our forces. We know here that the normal force is going to be pointing straight up, and the gravitational force will be pointing straight down, and we know this frictional force right here will be pointing to the side because it's the way it's pointing towards the center of the turn. And we know that the F net of y is going to be 0 because the car is not moving in the vertical direction. So we could go ahead and put the normal force minus the force of gravity equals 0. So we just solve this algebraically for n, and we know that n equals the force of gravity. Now let's look at the x's. We see here that the F net x is going to equal the force of static friction because this is the only thing in the x direction. So we know that the force of static friction equals mass times acceleration because force equals mass times acceleration. We also know that centripetal acceleration is equal to velocity squared over the radius. So we go ahead here and we know that we're gonna replace a with v squared over r, and we end up with the force of friction, static friction, equals m times velocity squared over r. Now we know this formula that the force of friction is going to be less than or equal to the coefficient of friction times the normal force. So let's go ahead. We've already solved for FFS here, so we're just going to go ahead and plug that in. Plug this in for the force of friction. So we're going to plug in m times velocity squared over r is less than or equal to coefficient of friction, and the normal force, which we found is equal to mg. So we're just going to solve this algebraically for velocity squared, and you end up with the coefficient of friction times gravity times the radius. We plug all these numbers in, and we end up with v2 is less than or equal to 171.5, and with the square root of that we end up with 13.1 meters per second as our velocity. Now in the second part, they're trying to find what is a safe angle to bank it so that we can go 13 meters per second safely. So we know that F net is going to be the normal force times the sine of theta to get us that x. And we know that force equals the mass times the acceleration, or like we found here, acceleration is v squared over r. Now we know that Fy is going to equal the normal force times the cosine minus this mg will equal 0. So we're just going to go ahead and algebraically solve that n cosine theta equals mg. And now we solve for n and find that mg over cosine theta equals the normal force. Now we're going to go ahead and plug this n back into this x equation. So we equal force equals mass times velocity squared over r, and we end up with mg cosine for that n times sine of theta equals the m over the velocity squared over r. And we solve this algebraically, and we end up with sine theta over cosine theta equals velocity squared over rg. Now we know that sine theta over cosine theta equals tan theta. So we know that tan theta equals the velocity squared over gr, which are gravitational force, and our our radius. And we just plug in these numbers, and we get 13 meters per second squared over 9.8 times 25 meters, and we end up with 35 degrees theta as the safe angle to travel.